This is screencast 1 for 571, week 3. So I'm going to finish working a little bit on Introduction to Statistics, and then I'm going to dive into control charts. So, statistics. So there's some words that need to be mentioned. Collect n observations on a random variable to form a sample of size n. So that's a phrase. So you don't say how many samples, you say how big is your sample. So you collect one sample and it's of size n, and that means it has n observations in it. The intention is to estimate parameters of the random variables probability distribution. With the sample. Also, test hypotheses about these parameters. With the sample. So really, statistics is all about probability distribution parameters. So the idea of statistics is, let's collect some data on a random variable and use the data to guess what the parameters are, and also to assess the validity of particular statements about the parameters of this random variable. So the key thing is that statistics is simply the handmaiden of probability. It's intended as a device to get at the truth of the probability distributions of the random variables you're observing. So if you don't get the probability straight, you don't know really why you're doing any statistics in the first place. Unfortunately, a lot of statistics courses get insecure about keeping students entertained, and they suppress the probability, and they focus on the graphical tools that statistics has to offer for doing this task of assessing probability distributions, but they don't really make it clear that everything is about the probability distributions. Partly because the probability is viewed as a mathematical topic, and there's a kind of a math phobia in the United States at the moment, which makes a lot of teachers uncomfortable spending a lot of time on the mathematics, i.e. the probability theory. But that's the whole point of doing statistics. There is no other point other than assessing parameters of probability distributions. This is going to be made very practical in the control chart section of this course. We are going to make management decisions based on what we think is happening to the parameters of probability distributions, of metrics that we are taking data on for the purposes of assessing the quality, which is really the profitability of our business processes. So we've got a basic setup in statistics. That if you keep this picture in mind, you will have a clear idea of what's going on whenever you assess some statistical tool that's being touted as the next great thing. And it's It's this picture. So these are uppercase. And these are lowercase. And they are realizations on the random variable. So this is the sample. These here are the random variables that are responsible for generating the sample. We assume that x, uppercase x1 through xn, we assume that these guys are all same distribution. Having made that assumption, we only have one set of distribution parameters that we need to assess. So the most common parameter to assess with the sample is the mean, mu. And the most common distribution to assume is, you guessed it, is the normal. So we assume x1 through xn are all distributed as normal with a mean of mu and a variance of sigma squared. So the game in business, turns out, is to view a metric as a random variable and let that metric talk to you, let that metric generate realizations, and then try to guess what the value of mu is and what the value of the variance is just using the sample. So the sample mean, x bar, which is 1 over n, sum I equals 1 to n of xi, is an estimator for mu. It's simply a way of estimating mu. It is not mu itself. X bar is a sample statistic. Now, I have used uppercase letters in my formula for the sample mean. And that's because I want to drive home the point that it's an estimator, not an estimate. An estimate of mu is lowercase. You collect actual data, and since we're speaking in general terms here, I have to put in a placeholder, as they say in high school, for the actual numerical values. So a lowercase x bar is simply a number that you compute by taking a bunch of numbers and averaging them, namely the n observations you have taken on the metric. So what's the difference? Well, the sample mean, uppercase x bar, is a random variable itself. So this guy is a random variable. And so it has a probability distribution. Another sample statistic, probably the second most popular one that you see, is the sample variance. And that is S squared equaling 1 over n minus 1 sum I equals 1 to n of xi minus x bar quantity squared. S squared also has a sampling distribution. So x bar is a random variable and hence has a sampling distribution. So sample statistics have sampling distributions. And this guy is also a random variable with a sampling distribution. So what does it mean by having a sampling distribution? And especially, what's the deal about, I thought you said we had a sample, and so we compute this one number. How can it have a probability distribution? The key is that we think about observing many size n samples. That's the key that needs to be appreciated. Statistics is not about what happens with one sample, what you compute. Statistics is about what distribution of values you would get if you were to repeat your experiment many times and then look at the distribution of values of your sampling statistic, of your sample statistic. Well, so folks tend to get bogged down with the computation from a particular sample of these numbers. Well, just for the record, let's say you have a sample of 2 observations. Then lowercase x bar is 5.5 if you've observed 2 and 9 as your 2 observations. And s squared, lowercase s squared, which is 1 over n minus 1, sum I equals 1 to n of lowercase xi minus lowercase x bar squared. In this particular setting, it's 1 over 2 minus 1 for this particular sample. It's 1 over 2 minus 1 times 2 minus 5.5 quantity squared plus 9 minus 5.5 quantity squared. That whole thing divided by 1. And that will give us the value 24.505. For this example, here's a lecture question. What is the sample standard deviation for this particular sample of size 2 with observations 2 and 9? What is the sample standard deviation? So the central limit theorem. Affectionately known as the CLT. Probably the most important theorem in statistics and the most important one for this course. It has a statement that is all about repeated sampling, and it goes like this. If the sample size n is is large, mu xi is finite, sigma xi is finite, then if x1 through xn are independent and all distributed with the expected value of any one of them equaling mu and the variance of any one of them equaling sigma squared, then x bar, uppercase x bar, is distributed approximately as normal with a mean of the constituent variables that you're observing, and a variance, which is the variance of the constituent variables you're observing, divided by the size of your sample. Now, the way this is usually presented in an effort to make it interpretable is to say, look, if you were to gather samples of size 47, say, and you were to gather, say, 300 of them, 300 size 47 samples, then since n is kind of large, 47 is kind of big, then if you built the histogram of the x bar values, you compute one for each sample, that histogram would look sort of like a normal bell curve. It would be centered at whatever the mean value is of the variable that you're observing, and the variance would be a variance which is small because it is the variance of the variables you're observing, but divided by the size of each sample. We are going to assume this distribution when we start building our control charts here in just a tiny bit of time. Now somebody says, well, there must be a condition on this distribution. No. Here's the end of the theorem. No matter what the true distribution of x1 is, and remember, they're all the same. And I had to say that, are independent and identically distributed. And all being distributed with a mean of mu and a variance of sigma squared. And here's a kind of a nice thing to keep in the back of your mind. When you know the mean, see, this is expected value, and you know the variance, that is not equivalent to knowing what the distribution is. You can have a t with 4 degrees of freedom and know the mean and variance, but that's a different distribution than, say, the normal. So, knowledge of the first two moments is not equivalent to knowledge of the distribution. And that's what the central limit theorem is trying to say here, that it doesn't matter what the distribution of x1 is. As long as you've got your first two moments being finite, you've got independence, and they're identically distributed, then this will hold. This was proven around 1936 by a Russian mathematician, and a lot of people had tried to prove this earlier and had failed, but Kolmogorov was able to push a proof through, which had been an open problem for about 200 years. People suspected it was true, but no one could mathematically show it. This is not an academic thing, because without this theorem, most of statistics is simply an opinion. With this theorem, statistics is actually a valid way of assessing how much you know something. So with this theorem, statistics became a way of discovering knowledge. Up until that point, statistics had been kind of a curiosity that some people proposed as a good idea and other people said it really doesn't work. So it was very important, 1936, that this became part of the known mathematical literature. And this really is the beginning of statistics. And from statistics, of course, we have, as you saw, actually jumping the gun a little bit, Shewhart starts proclaiming the wonderfulness of control charts in around 1931, actually just a little bit before Kolmogorov had finished his work. And actually Shewhart was depending upon Kolmogorov's work, as we'll see in the next screencast. So actually, what Shewhart did was rather edgy. He is speaking for Bell Labs in the early 1930s about properties which were only starting to be talked about at mathematical conferences. So he was really kind of breaking new ground. And it seems for us now that this stuff is dated and old-fashioned and mired in boring numbers. Actually, there's nothing, it couldn't be further from that. This is a very adventurous and a little bit out there approach to running a company, using some mathematics tied to some statistical procedures. If the properties of these methods are not well understood, you would be ill-advised as a senior manager to put the profits of your company at the mercy of some of these techniques that are taught in this course. So here is the setup that Shewhart advocated. He said a process is in statistical control if its distribution is stable. And this is discussed in Ryan on page 26. So right off the bat here, there's a little lesson. When you see the word control in quality control, you want to put the word statistical in front of it in your mind, because it's simply a shorthand for statistical control. So when we use the word control in business, we're actually talking about a statistical concept. So, 210 is a little annoying. This course can be annoying with its mathematical stuff. But if you think about it, the world, at least the Western world, has decided that statistical control is what we mean by the word control. So this is a fundamental idea. It's kind of like if you want to learn French, you have to learn their verb structure, which is extremely complicated and annoying, but there's no way around it. If you don't understand their verb structure, you can't speak French. It's the same exact deal. What does that mean? Well, for the normal distribution, to take a specific example, this means that mu and sigma squared are constant across time. End of the first screencast.